Welcome to atoms. So for chapter 6, you're going to need an alphabetical list of the atoms and a periodic table. And both of these are provided in an appendix at the back of the textbook. But bear in mind that the periodic table you should be using while you study should be identical to the one that you'll be allowed to use on the quizzes and tests. So you should attempt to get from your professor or instructor the actual periodic table that you're going to be using, or at least one that's very close to it. That may or may not be similar to the one in the back of your textbook. So let's go over some terms and definitions that are going to be useful in your study of chemistry. So matter is anything that has mass and volume. In other words, matter is anything that has mass and takes up space. This is basically everything that you see with the exception of light itself. So chemistry is mostly concerned with the measurement and description of matter and its interaction, so how it changes. So these are chemical reactions between various substances. On Earth, nearly all matter is composed of extremely small particles called atoms. And atoms, we will define an atom here as a particle with a single nucleus plus the electrons that surround that nucleus. So there are only 91 naturally occurring types of atoms or elements on Earth, and there are about 20 more man-made ones, man-made elements that have currently been made, and they're man-made in the sense that we basically, in a particle accelerator, we take two smaller atoms and we smash them together, and every once in a while they'll stick, they'll react together. Most of the time these are fairly radioactive, which means that they're unstable. They break apart after usually a pretty short period of time, less than a second generally, although some of them are a little bit longer lived. All of the millions of different substances that exist on Earth are then composed of different numbers and arrangements of these roughly 100 types of atoms, these roughly 100 elements. Each element is represented by an element symbol. The element symbol is either 1 or 2 letters long. The first letter is always capitalized, the second letter is always lowercase. If you mess these up and you capitalize the second letter, that means that you've essentially made two elements, one whose element symbol is just the first letter and one whose element symbol is just the second letter. Now those won't necessarily always be valid element symbols, but you're at least indicating to the reader that there are two different atoms there if you capitalize both letters. Note that while the book uses the terms atom and element interchangeably, your later chemistry courses will probably draw a distinction between these two terms, and thus I'm going to try to keep the two terms separate. And also, you are probably best off if you use the word element when talking about a type of atom, and the word atom when talking about a single particle of some particular element. And this is I'm going to try to make that distinction in my videos as well. So now let's talk about electrical charges. So some particles have a property called electric charge, and there are two types of charges, positive charges and negative charges, and they interact with one another. So like charges repel, which means if we have two positive charges, they're going to push away from each other. Opposite charges, if we have two negatively charged particles, they will also push away from each other because those are like charges. Opposite charges attract, so if we have one positive charge and one negative charge, they will attract and they'll both tend to move towards each other. Uncharged particles, in other words those with neutral charge, they don't attract or repel each other. So they'll just sit there not influencing each other at all, at least not electrically. All right, now let's talk about atomic structure. So atoms are composed of 3 subatomic particles: protons, neutrons, and electrons. The proton, which we symbolize with a P+, has an electric charge of +1, hence the plus sign on there. And each proton has a mass of roughly 1.0 AMU, where AMU stands for atomic mass unit. The protons are in the center of the atom, called the nucleus. And while the atoms themselves are very, very small, the nucleus is very tiny in comparison even to the atom. So atoms are really, really small. We can't see them with our eyes. They are much, much smaller than even the cells of our body are. So my hand is composed of lots of different living cells. Each of those cells is composed of many, many atoms. Each atom has just one nucleus in it, but that nucleus is really, really small in comparison to the atom. The atom is really, really small in comparison to the cell is really, really small in comparison to me. So atoms and nuclei are really, really tiny. The number of protons in the nucleus is called the atomic number of the atom, and the atomic number is symbolized with a capital Z. Now, the number of protons, the atomic number, determines the identity of the atom, and thus its name and its symbol, which is why the atomic number is a special quantity for us. The number of protons is never changed by chemical reactions. We can change the atomic number by nuclear reactions, but in chemistry, we generally aren't dealing with nuclear reactions unless we're specifically talking about nuclear chemistry. The neutron, which is symbolized lowercase n with a superscript 0, has an electric charge of 0, which is why we have the 0 on the upper right, indicating its charge, which means that it has no charge. It's neutral, hence the name neutron. Each neutron has a mass of 1.0 AMU, just like the proton did. So, as far as chemistry is concerned, the only difference between a neutron and a proton is that the proton has a positive 1 charge, the neutron has a 0 charge. And the neutrons are also in the nucleus along with the protons. Now, the number of protons plus the number of neutrons in the nucleus is what's called the mass number, or the mass of that atom. So you could call this the atomic mass, although we'll get back to the true definition of atomic mass a little bit later on. So the atomic mass, or the mass number, is symbolized with a capital A. And neutrons act something like the glue of the nucleus. Because protons are positively charged, that means that if we have 2 protons in the nucleus, they should fly apart. They should tend to fly apart, because they're going to repel each other. But the neutrons hold the protons in place. Now, they don't do this electrically. They do this through what are called the strong and weak nuclear forces, which I don't really want to get into now, but it's enough to say that the neutrons act to hold the protons in place in the nucleus. So the number of neutrons is never changed by chemical reactions, just like the protons are never changed by chemical reactions. Again, they could be changed by nuclear reactions, though. The neutrons have little influence on the chemical behavior of the atom because they're not charged. They're not influencing very much, except for the stability of the nucleus, which again in chemistry, outside of nuclear chemistry, we're not really that interested in. So there are a few cases where the neutrons influence chemical reactions, but the effect is generally pretty small, and it's usually small enough that you shouldn't worry about it for at least a first-year chemistry course. There are some cases of where an atom of one element with more neutrons may be more or less likely to react, and it can then be selectively bound in organisms to different rates, but those effects are generally pretty small. All right, now let's turn to the electron. So the electron is symbolized with an E and a superscript minus, and that's because the electron has a charge of -1. So our proton, neutron, and electron have a charge of +1, 0, and -1. Each electron has a very small mass, about 0.00055 AMU, so the electron weighs far, far less than the proton or the neutron. It's about 1/1800th or so of the mass of a proton, so it's the mass of the electron is really small, although the charge is exactly the same magnitude. So because the electron mass is so small, we generally ignore the mass of the electron when finding the mass of the atom. That is, that nearly all of the mass of the atom is in the nucleus, because the electrons are not in the nucleus. The electrons orbit outside the nucleus in regions of space that we call orbitals, or the electron cloud. So the electron orbitals are very large in comparison to the size of the nucleus, but the electrons themselves are actually really, really tiny. And so most of the volume of the atom is in the orbitals, but the orbitals themselves are mostly empty. They've got some electrons in there, but the electrons are so small that essentially the vast majority of an atom's volume is just empty space. And we've got this tiny little nucleus that contains almost all of the mass, And then out there around the nucleus are some electrons that orbit the nucleus, but those electrons are so small in relation to the space that they take up that essentially that space is empty. So the number of electrons can be changed by chemical reactions, and in chemical reactions, these are really the only things that are moving around or that are being changed in atoms. So electrons are the only subatomic particle gained or lost in chemical reactions. So now let's turn to neutral atoms. If an atom has equal numbers of protons and electrons, because remember that the proton has a +1 charge and the electron has a -1 charge, if they have equal numbers of positive charges and negative charges, then the overall charge is 0. This means that the number of positive charges equals the number of negative charges, and the net charge, or the overall charge of the atom, is 0. We say that the positive and negative charges are canceling to produce an electrically neutral atom. Note here that some textbooks use the term atom to mean electrically neutral atom, and use ion to refer to any atom that is not electrically neutral. In contrast, textbook authors Dahm and Nelson use the term neutral atom to refer to a neutrally charged atom and an ion, and they use the term ion to refer to an atom with either a positive or negative net charge. So they use the term atom without the neutral part in front of it to refer to any atom regardless of its charge. So whether it's neutrally charged, as in their term neutral atom, or whether it's an ion. So they're using the term atom just to mean the particle, but not saying anything about whether its charge is 0 or not. Other textbooks may use the term atom to refer to just a neutral atom, and may use the term ion to refer to atoms that are not neutrally charged. The textbook that I use for general chemistry, which is Zumdahl's Chemistry and Atoms First Approach, does make this distinction between atoms and ions, and so generally I'm going to try to use the term atom to refer only to a neutrally charged atom, and the term ion to refer to an atom with either a positive or negative net charge. So if you notice that my terminology is differing slightly from the textbook, this is likely why, is that I'm trying to keep the terminology the same as the general chemistry textbook that you would be using in the next course in sequence. So let's look at some more terms and definitions. For chemical reactions, a chemical reaction does not create or destroy atoms. It only rearranges atoms. So this rearrangement can change the identity and properties of substances involved in the reaction, but because we're not creating or destroying any atoms, we're just rearranging them, the component elements, those component atoms must still be there. We're just rearranging them, bonding them in different ways. So a physical change is a change in a substance that does not alter its identity, and thus it's not a chemical reaction. So one example of this is cutting a piece of paper or ripping it in half. In each of these cases, I still have exactly the same amount of the material as I did before. I've just changed the way it looks. I fold a piece of paper or I cut it in half. I still have just as much paper as I did before. It's now in a different format. So some other examples of physical changes include melting ice to form water, freezing water to form ice, cutting paper, folding a blanket, hammering a nail into a piece of wood. In each of these cases, the before and after substances are still there, just in a slightly different form. In this case, we've combined the nail and the wood. In this case, we still have all of those water molecules that were bound up in the ice. Now they're just able to move around in the form of liquid water. Ions, I've already talked a little bit about ions. In a chemical reaction, the number of protons or neutrons in an atom can't change, but the number of electrons can change. Which means that the atom can gain or lose electrons. And any particle, whether a single atom or a group of atoms that has a non-zero charge, is called an ion. Now the only way to have a charge of 0 is to have equal numbers of protons and electrons. And any particle with unequal numbers of protons and electrons will have a non-zero charge, a net charge. Now it may be positive if we have more protons than electrons. It may be negative if we have more electrons than protons. Any particle that has lost one or more electrons is a positive ion. This is called a cation. Now, it's a cation, it's a positive ion because we've lost these electrons. If we lose electrons, we're losing negative charge. As we lose negative charge, the overall charge on the ion has to become more positive because we already have some protons around and now we have fewer electrons to balance them out. On the other hand, a particle that has gained one or more electrons is a negative ion, because now we have more electrons than we have protons, we have more negative charges than positive, which means overall the charge is going to be negative. An ion does not act the same as the uncharged atom does, or a group of atoms, that it's formed from. That is, ions have different chemical properties than the neutral atoms or compounds of the same element. When writing the symbol or chemical formula of an ion, we must include the charge. We must write the charge as a superscript to the right of the symbol, just like we have the plus on P plus for proton or the minus on E minus for electron. That is, you have to write the sign and number of the electrical charge on the top right corner of this symbol for that ion. So let's look at some examples of atoms and ions. Any atom with 16 protons in the nucleus is a sulfur atom, which we symbolize with a capital S. An electrically neutral sulfur atom also has 16 electrons to balance out those 16 protons in the nucleus. The symbol for such an atom would be just a capital S. Note that we could also write this capital S with a 0 superscript if we wish to stress that the atom has no net charge, although writing that 0 is optional. It's not necessary. A sulfur atom that has gained 2 electrons, on the other hand, is called a sulfide ion, and the symbol for that ion is S2-, because now the charge is 2-. We've added 2 electrons. Each electron is adding a charge of 1-, and remember that with an ion, we don't have a choice about writing the charge. We have to write the charge. Otherwise, if we don't, then the reader has to assume that we're talking about the neutral atom. And so, with our ion here, S2-, we've got to write that 2-. There's also another thing I'd like to point out, that when we're writing charges on ions, if we're writing a charge, as in this case, we write the number first and then the sign. We don't write it with the sign first and then the number, as you would generally see in mathematics. And this is because this symbol over here represents an ion, and the symbol on the right represents something different in chemistry. This represents an oxidation state, which is not necessarily the same as our charge. And I don't want to talk any more about the oxidation state for right now, because it's beyond the scope of this video. So any atom with 19 protons in the nucleus is a potassium ion atom, and we're going to symbolize that with capital K. An electrically neutral potassium atom has 19 electrons, and the symbol for such an atom is capital K. We may or may not write the 0 on top as a superscript, but a potassium atom that has lost an electron is called a potassium ion, and if it's lost 1 electron, then there's 1 more proton in the nucleus, then now we have electrons, and so that means that we have a +1 charge, so we have to write K plus. Alternately, we could write that K 1+. Whether we write the 1 or not doesn't matter, because if we just see a plus or just a minus, we assume that it's a +1 or -1. That was atoms.